Hello everyone. In this video, we are going to talk about uncertainty propagation in mobile robot odometry. The material, as with previous lectures, is taken from the amazing book, Introduction to Autonomous Mobile Robots by Sigurd Norbash and Scaramuza. So there are a few things that we need to talk about. If you watched my channel, under playlist robotics, I have a video about kinematics of mobile robots and odometry. So you can consider this video to be like complementary to that. Because in that video, we showed the equations of motion and simulating that and so on for a differential drive robot. But we mentioned the fact that there is drift and the actual path of the robot and the one that we perceive or simulate or calculate will not be the same because of so many sources of error. So in this video, we're going to talk a little bit more about those error terms, and we come up with a formulation for that error. We want to come up with a covariance matrix, and we want to show that, for instance, as the robot moves on, whether it's on a straight line or curve or something, the uncertainty in the location of the robot or the pose of the robot in general is going to get bigger and bigger. Okay, so you are less certain about where the robot could be because of the error. So we want to model that here. So first thing I want to emphasize is maybe in previous videos we used the word odometry and the word dead reckoning kind of interchangeably. These two words, although almost similar, they are not identical. So what's the difference between them? Odometry means to calculate the pose of the robot, in this case x, y, and theta for a planar differential drive robot, with only the wheel encoders. So you just count the rotation of the wheels, and based on that you calculate the x, y, and theta, and that is exactly what I did in that video I just mentioned. That is dead reckoning. Now, if you also, in addition to the encoders, you bring in the heading sensors, okay? If you can bring in the heading sensors, like for instance, a magnetometer or gyro or anything that can measure the angle as well, okay, and kind of add that, that is the dead reckoning based on the definition given in this book. Okay, so what we are mostly working right now is odometry here. Okay, we are not looking into heading sensors, and we just look at the encoders. So first of all, when we say there are errors in these calculations, what are the sources of these errors? Let's take a look. One of them is, of course, limited resolution during integration. When you are approximating, for instance, dx over dt, you approximate it by delta x over delta t. This is assuming that this delta t is very, very small for it to be accurate. But the thing is, any encoder, any system, any sensor actuator, they have a limited sample time, and that makes this just an approximation and not be accurate. Okay, also your sensors or anything that we are not working with them necessarily, but they all have a resolution that is limited. So the other thing is the wheels might not be perfectly aligned. When we looked at the mobile robot, we assumed that these two wheels, right, if you look at their axes are perfectly on the same line. Okay, and so they both move on two parallel lines. In reality, it might not be perfect, especially if these wheels, their axes, have a little bit flexibility in it. The other thing is the wheel diameters. Do we know them exactly, and are they the same? Not always these two wheels are perfectly the same diameter, and it's not like one of them is like 5 centimeters, the other one is 10. No. But for instance, one of them could be 5.00, the other one be just like 5.02. And although that is very small in terms of centimeters, over time it will accumulate. Okay? Then variation in contact point of these wheels, we always assume that these two wheels are on the same surface. It's not always the case. Okay? And so they both have the same friction, the same traction force, they both do not have any slip, and something, the surfaces of planar, these are not the case. Not all surfaces of planar, there is always slipping that is happening, and the more slippery the surface is, of course, the bigger the slippage. And some of these contact points on one tire and the other one could be a little bit different, and that's enough to give it a little bit tilt or a little bit more traction on one side than the other, and so unequal motion on the two sides even when you commanded it. So some of these errors are deterministic or systematic, okay, which you might be able to eliminate if you perfectly calibrate the system, if you make sure the two diameters are very, very, very close, the wheels are to the best of your capability aligned and something. These are the ones that you can determine and you can hopefully eliminate, okay? But some of these are random and they are or non-deterministic, and you cannot necessarily always get rid of them, okay? For instance, the slipping is not something that you can deterministically calculate, or a variation in the contact points or something. These are not something that you can perfectly get rid of. So in that case, although you get some pose, x, y, and theta, for each one of these variables, there is a degree of uncertainty, okay? They become some random variables now, and if they are, then you can add basically a variance for each one of them, and for the whole pose, you can add a covariance matrix, and you want to see how this covariance matrix behave over time, okay? So, from a geometric point of view, we can break down the sources of error for a mobile robot, like a differential drive robot, into three major ones. One is the range sensor. What is range error? I'm sorry. Range error means what? Means the errors that you have for the distance traveled by the robot, some of the wheel's movement, okay? So this distance that is traveled, like by each one of them, if you call this delta S left and this one delta S right, then how much these have basically traveled, and based on that, the delta S of the robot, which is the average of the two, correct? How much that one is traveled over time, that is something that you can have error in, and we mentioned why, because we are integrating numerically. Then we have turn error. So this is when you start to turn, which most of the time happens, and that is because the wheel motions are not necessarily the same, okay? Whether they are not perfectly aligned, whether there is a slip on one side and or more than the other side is, okay? And there is drift error. Drift error is in the error of the wheels, okay? And typically that comes from reading the sensors, and again, it could be also due to slipping, which causes error in the angular position of the robot. So the important thing is the effect of the drift and turn over time is bigger than the range, because if you look here, let's say I move on a straight line, I come all the way to here. Now I might have some error, so it could be here or it could be within this range. Okay, so I have this much of uncertainty about the robot position, but when it turns, when it starts to turn, now the X and Y position of the robot is not just going to be that V times fixed cosine of theta. That cosine and sine of theta are changing now, so the effect is going to be more dramatic. So here you might get basically a bigger radius over time, and it starts growing bigger because when you use this cosine theta and sine theta, their effects are nonlinear. Okay, but the effect of delta S, as you can see on delta X and delta Y, this effect is linear. But these effects of angle, which can come from turn or drift error, that is nonlinear. So over time, they will contribute more. And you might see that in something like here, although I'm gonna simulate this for you and go through equations of that. But here you see, here I'm going straight, here I'm going on a curve, and here I have a bigger chance of increasing the uncertainty. And you see, like, if you look at the number of steps, right, you see that, for instance, here is after 7 steps starting from here. This is kind of the uncertainty you have here. You have this one, and this one you can see is quite a bit bigger. Or if you compare this one with this, you can see that the effect of them is kind of more pronounced. Now, how do we exactly formulate this? So, of course, we have to start from the odometry equations and go from there. So here, if you watch my previous video on odometry equations, you know that the pose of the robot is x, y, and theta. And delta x is going to be delta s times cosine of the change in the new angle, right? And you might say, what is the new angle? Is that theta plus delta theta? Yes, and the previous angle is just theta. So here you see we are using the average of the two angles, okay? Because you are right now here in position x, y, and theta. And then when you move a little bit and come here, now your x goes to x plus delta x. And this is going to go to y plus delta y, and then theta plus delta theta. So your theta x and y is constantly changing. So if you want to just look at delta x and delta y as a function of theta, because remember x is basically v cosine theta, or x dot, and y dot is v sine theta. If you want to integrate these versus time to come up with delta x and delta y on the left side, and v, which is delta s over delta t, be delta s, since this cosine theta goes from theta to theta plus delta theta, I have to use the average of the two, which is theta plus half delta theta, to get an approximation here. So this is the change in x because of the travel delta s and change in the angle. This is the change in y for the same change in parameter. By the way, since I mentioned that my previous video several times, this is that video, okay? Kinematics of differential drive robots and odometry. So here you see, you can see x dot and y dot and change in x and y and everything. So it's a good idea to watch this video before coming to this one, because this one, as I said, is like the secondary or complementary video to this. Here we went through equations and simulated, but here we're going to talk about the propagation of uncertainty in those equations. So this is the change in x and y, okay? These are the things we have, and p is the pose of the robot. Good. Now what? Now, in here, there are two parameters in these equations, delta s and delta theta, these two. These can be written in terms of the distance traveled by the left and the right tire. As I said, if you call this delta S of left and call this delta S of right, then delta S, which is for the centroid, is going to be the average of the two, and change in the angle is going to be the difference between the two divided by b. And b here is the distance between the two tires, okay? So again, these two are in that previous video. So this is what we had. Now we are going to get the new position based on the old position. So if old position is p and the new position is p prime, which is x prime, y prime, theta prime, we want to use these update equations, get there, and then based on that, we go and look at the uncertainty equation. So p prime is p plus the change in x, y, and theta. This is the change in x we had up there. This is the change in y. This is the change in theta. Okay? So you can see them right here. And then, and p is of course this. Now for those we just replace, and then here in place of delta theta and delta s, we're gonna pick these two and place it. So your new position p prime is going to be this, okay? This is your new position in terms of the displacements of the tires. Now, what do we do? We say, well, look at P prime. It's a function of 5 parameters or 5 variables here. X, Y, theta, displacement of the right tire, displacement of the left tire. If you look at your equations, you see these 5 parameters everywhere. So I can say this is a function of 5 variables, this P prime, yes? And then these 2 displacements of these 2 tires, I put them in a vector, call it delta RL. Okay, the displacement of the right and the left tire, I put it in a vector, and so this is a vector here. Now, what is it that I want to find? I want to look at the propagation of uncertainty into this guy here. Well, where does that come from? Well, it comes from the uncertainty in each one of these 5 parameters. None of these 5 parameters is known to the last digit, okay? They have uncertainty. It's uncertainty in the previous one plus uncertainty in how much each tire has moved, okay? Yes? If I call this P and I call this delta RL, you see that P prime is a function of P and delta RL. So because of uncertainty in each one of them, this P prime will have uncertainty, okay? And if that's the case, then we can use our calculus to calculate the propagation of uncertainty. But before I go through the formulation, I want to look at the assumptions with you so you know which kind of assumptions we are using. 1, we assume that the errors of the wheels are independent from each other. So if you look at the covariance matrix of delta SR and delta SL, it is going to be a diagonal matrix. These two are what? 0 because they are independent. So one, tire left and tire right uncertainty will have no effect on each other. Okay, that's the first thing. Second thing is the variance of error for each one of these wheels is proportional to the absolute value of distance traveled, and that is exactly this portion here. Look, if you look at these diagonals, they are proportional to this distance traveled, and the proportionality constant is called k right and k left. And these are not known values. You have to determine them experimentally, okay? But you see that they are proportional to the distance traveled. So the further these wheels travel, the bigger in a linear manner the covariance becomes, okay? And this is relatively a good assumption. They could be not perfectly linear, but we can consider that to be a simple linear for now. The other thing is, we said P prime is a function of P and delta RL. Although each one of them, they have their own uncertainty, but there is no correlation between them. So the correlation, the covariance of delta RL and P, they are not related to each other. And finally, when I want to derive the uncertainty in anything, here I use first order Taylor approximation, and that is exactly what you can see here, that the covariance of P prime is what? Is the del of f. F is this function with 5 variables, right? Which is basically these guys. And as you look, f has 3 components in it, f1, f2, and f3. So del of f with respect to p, of course, right? Partials of f with respect to p, which means partials of f with respect to x, y, and theta, because x, y, and theta are the components of p, right? So partials of f, this is basically a Jacobian matrix, times covariance of p, the uncertainty in p, times the Jacobian of f with respect to p transpose, okay? And then what? A similar term for the delta RL. So partials of f with respect to delta RL on the left and transpose of it on the right, and in the middle is the covariance of the wheels for the distance traveled, okay? And you see here, I'm just using first order terms. There is no second order term, and so that is exactly what I'm doing here in this Taylor approximation. Now, what are these entities here? Sigma delta, sigma p, and these Jacobians, what are they? Well, the first one is this guy here. This one is, of course, partials of f with respect to p, as I said. So it's partials of those three functions with respect to x, y, and theta. And so because there are three f's and there are three components in p, so this guy is going to be a 3 by 3 matrix, as you can see, right? That's the first column, second column, first row, second row, third row. Okay, so it's a 3 by 3 matrix. All you need is to take partials of f with respect to these parameters. For instance, the first column is partial of f with respect to x. So let's go ahead and look at this one just as a practice. So if you look at this here, what do I have in this first row as partial with respect to x? Well, this whole first row there is only one x in it, and it's a linear term, so partial of it is going to be a 1, and that's exactly what you can see over here. But the second row and the third row, if you look at them, there is no x in them, right? Look at the second row, there is no x in it, so partial of that with respect to x is 0, and this last one is also 0, okay? So clear. Then we repeat that, we go first, second, third row. This time we take partials with respect to y, and then we take partials with respect to theta. For y is going to be similar, so it's going to be 0, 1, 0, as you expect. But for theta, the thing is, for theta, that's not the case, because although this last row has a 1, but these guys, there is cosine theta and sine theta. So we have their derivatives included, and those are these guys. Well, of course, the delta S and delta theta have to be replaced by these two formulas to get those. So that's that Jacobian, okay? So we got this taken care of. Then what? Sigma p. Well, sigma p is the covariance of basically the same thing in previous iterations. So here, in order for us to use this, because now this is going to be an iterative equation, correct? This is going to be an iterative equation. I have to know sigma of p at some point. Let's say at time 0, this is known. Okay? So I can use this as an iterative equation and keep iterating that and calculating the new one. So I have to know that at some point, and let's say we go with some known one at time 0, and we can, at time 0, really we want to start it very, very small, because at time 0 we are relatively certain in where we are. So this one is now also known. Sigma for the wheel motions is already assumed. As I said, this KR and KL, they have to be determined experimentally. Now for simulation, we just plug in numbers, but in practice, we have to calculate them, okay? So the last thing we need to find is this partials of f with respect to the tire motions, delta SR and delta S left. So that's what we are. And again, we go and look at the rows of f, take partials here. Now, since you have 3 f's and 2 deltas, if you look at your matrix here, it has 3 rows, but it has 2 columns, okay? So this 3 by 2. And if you keep going, and if you look at the dimensions, so we got this, right? We just take partials of those 3 rows with respect to delta SR and delta SL, and you get this one. And now if we go back and look at our update equation, correct? Let's look at this recursive update equation. Let's make sure all the dimensions match and everything, correct? So what do we have here? This one, as we said, is a 3 by 2. This is a 2 by 2. This is a 2 by 3. This guy is a 3 by 3. This is a 3 by 3, 3 by 3, and this is also a 3 by 3. So you get a 3 by 3 matrix, and the diagonals of that are going to be the covariance for x, the variance, sorry, they're going to be the variance for x position, y position, and theta. So if we want to draw these ellipses, all we need to do is to basically draw an ellipse with this diameter to be proportional to the x and y variation, and for the angle also we can do that as well, but here I guess it's just x and y, otherwise the angle of them will be a little bit different, and you can basically have the ellipse also a little bit tilted. So these are just showing the variance in x and y on just the position. Now, for the sake of a simple robot, some of the terms here will be a little bit simplified, like which ones here. So if we look at these, because this is very clear, okay? And this one is known, so all we need to look at are these guys. Well, this one is very clear. This delta, theta, and delta S are coming from these two calculations, right? So they are coming from here. So we just plug them in, and so that Jacobian is good. This covariance, if we have KR and KL, is also good. The last part that I want to take a look with you is these terms here. This guy here, right? And then a similar one for delta SL, this one here. And then this one here. And this one. These four partials are what? So partial of delta S will with respect to delta SR. Well, if we go and look at here, we can exactly see what it is, right? What is it? If I take partial of delta S with respect to delta SR, the same that I do it for delta S left, you clearly can see that it is 1/2. And if I do delta theta with respect to these, you see it's either 1/b or negative 1/b. Okay, and these are exactly these ones. So these guys will also go there, and now I have everything. My update equations are ready. All I need is to simulate them. And here I wrote a MATLAB code for you that simulates both of these, straight motion and motion on a curve. I have parameters here, okay? So there is this b here and the number of integrations, right? So b is that number, and then you can see that these equations are all created, and then here you have your confidence started and then propagated. Okay, and these are the motions that you have. So one of them is a straight curve where both of them go at the speed of 0.1, and then the next one goes 0.1, one goes 0.11, so it causes it to curve, right? And you see that initially, if you look, the average of those states, x, y, and theta, is 0, 0, 0, and the covariance of them is 1/10 to the -6. So I'm pretty much very certain about where I am, x, y, and theta. But over time, this sigma starts to grow. Okay, the sigma starts to grow. So let's go ahead and run that so we can see the result. There we go. So this is the first one here, going on a straight line. You see the ellipses are getting bigger and bigger. And look at the progression. It's huge, actually. Okay, so although initially I was almost perfectly sure where I am, it just takes a little bit movement, like 10 meters. I go in the x direction, and now I'm not sure about my y direction by ±3 meters. That's huge mistake. Or not mistake, actually, huge error. Sorry about the term, that's huge error. And here is the basically going on a curve. And again, if you compare this ellipse versus that, you see that it is actually quite bigger, especially in this kind of transverse direction. It's quite a bit thicker than this one is. Okay, so when you're turning, your calculation errors are going to grow much bigger than when you go on a straight line. So drift and turn errors are more dramatic than just going on a straight line. I'm going to share this file with you under video description so you can play with it and learn from it. So hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.